Hi, my name is Joel Chatfield, and this is the Lab 3 Black Hole Gravity Lab. So the introduction, this lab consists of two experiments. One is using the location of orbit and mass of a star to find the net force of the black hole on the star, you will then use to find the mass of the black hole. And the second was using the mass of that black hole to find the velocity needed of a ship launching off a planet to escape the black hole's orbit without crashing into it. Then the trajectory of the star was made using random number generation. Um, so the base concept of this is using Newton's second law along with circular motion, the force acting on it, to determine um, how the forces how the mass creates forces. And then these are the equations you use. And the assumption there we use is that because it's not a real orbit, we have to take the mass of the black hole determined by the force at set points and then average that all out to create a semi accurate representation because it's not a real orbit we can observe. Here's the code for the first part. So we used, these are the base vectors and trajectories used for a lot of them, and then these are delta x and delta y, which are determined iterations. And then these are the vectors. The initial vector is the previous amount, the previous value for x and y, and then final is the current value. And then change is final minus initial, and the momentum is just going to be initial and final times the mass of the star to find its momentum. And then F net is going to be equal to the derivative of momentum, which is just going to be the change in momentum of the change in time due to averages because we don't know the exact equations. P hat is just P initial divided by the magnitude of P initial to get a vector of size 1 in that direction. And then the derivative of the magnitude is going to be the change in magnitude divided by delta t. And then the dp dt parallel is p hat times derivative of magnitude. That's also the same as f net parallel. F net perpendicular is going to be f net para is going to be the same thing as the derivative of momentum perpendicular, which is total derivative of momentum minus derivative of momentum parallel, which is going to give you a final number because those two add up to be total momentum. And then mass of the black hole is found using the F net equals g mm over r squared equation, which will solve out for one of the m's. And then the program ends up looking like this. Goes in a circle. The orange arrow is total force. Cyan is perpendicular. Magenta is parallel. And then, of course, we also have the second equation, which the code for the equation looks very similar. You just find the effects of forces on the ship and the planet by black hole and each other. And then you end up with this final representation. That small cyan circle is going to be the movement of the planet, and then the magenta line is the total distance and motion created by the ship. And basically what happens is the ship fires itself and uses its velocity to go very close to the black hole, and then uses the force of the black hole plus its initial velocity to slingshot itself out of orbit, with the force of the black hole allowing it to accelerate enough, plus its initial momentum. And then we're going to, what does it mean? How do the components of the force differ from components of rate of change? Conceptually, they're the same, like mathematically speaking. Newton's equations actually has them to be the exact same. Force is considered the change in momentum via time, and how momentum changes because they're both, just like acceleration is change in velocity. It's the same thing. You're just adding mass to both these things. However, force can be viewed as the cause of change. Force is what makes something's momentum and velocity change, whereas change in momentum can more be viewed as the effect of the force. And last but not least, what if? What velocity would the ship need to stay in orbit and not run into the planet? This was calculated out using simulations. It's right here. It's negative. It is slightly faster in the negative direction, but more importantly, is much more positive in the a lot more force in the y direction, which will allow it to enter a larger and slower orbit than the planet, so that it can orbit but not run into the planet. This has been my lab. Thank you very much.